Alrighty. I will begin. Heavenly Father, we thank you for your creation that we can study. Help us to just glorify what we do and just understand a little bit more about physics today, Lord. In your name I pray, Lord Jesus. Amen. So, yes, I guess it's good news. I think you guys can get jobs in 4 years from now. So, or in about 2 years, maybe. Somebody else.
How long were you up last night?
Huh?
How long were you up last night?
Yes. So, I mean, come on, you got to stay up for like the historic third term, you know? He's just third. He won his third term. His third term. Well, he's won 3 times now. So, inductance. That's right. I said it. Okay, so it's not been proven. I don't care. Shut up. Sorry. So, inductance is defined to be in terms of a proportionality between the magnetic flux in a coil. In particular, we're going to talk about, to start with, is self-inductance. So, let me write this out here. The magnetic flux through a coil is proportional to the current I traveling through the coil. All right. We define the self-inductance L with that in mind. And here it is. So flux through the coil, phi B, is equal to self-inductance L times I. Now, my apologies, as I have inadvertently used L for the length of certain coils, which is sort of an unforced error. I mean, I should not have used L, capital L, for the length of any of these coils. That was poor planning on my part. When I type up my notes, hopefully I'll fix that. I don't think I'm the only one doing it, but it's a bad idea, because this is the inductance, which is the proportionality constant. So here we're talking about, you know, we've got, let me draw a picture. So we got some coil, right? So you've got a current going through it, right? You have the magnetic flux going through the coil. And let's see here. If the current's going as I've pictured it, which direction does the magnetic field go? To the right, right? So I've got my magnetic field lines in here like that, yeah? All right, so that's definition of inductance. The units for inductance, this has units called Henrys. I think I spelled that right. Oh, my bad. Henry. Actually, I don't know. Do I trust my notes? Somebody want to Google that? What's the spelling of Henry?
That's right.
Like that?
Yeah.
Oh, okay. Yeah. See, my sister-in-law thinks this is hilarious for some reason. I don't understand, but it strikes her as very, very funny that there's a unit of physics called a Henry. But, I mean, there it is. So let's work out example 1. What's the inductance of a solenoid? All right. So what was the, I drew the picture over here, all right? So let me make example start over here so I don't have to draw the picture again. All right, continued. Remember, we worked out before that the magnetic field is mu naught Ni, all right, from Ampere's law, where N is the number density, right? In this case, the flux, right, was equal to NBA, right? So here N is the what? Yeah, number of coils, or loops if you like, number of coils. B is the, field inside the loops, inside the coil, right? And A is the cross-sectional area of coil. So we're assuming, of course, also to write this, the very nice case that the solenoid is nice and long compared to its radius, right? So we have that the magnetic field is essentially constant, all right? We make that assumption here for the sake of simplicity. Wonder what would happen if I didn't make the simplifying assumption and actually did the calculus here. Okay, I'll stop. Here, N is also equal to N divided by, I'm going to call this L. This is now our newfound symbol for the length of the coil. All right. So N also enters there. All right. So let's put it all together. We've got the magnetic field, the magnetic flux phi b is equal to N times mu naught little Ni, all right, which I could, that of course is equal to L times I, right? By definition is equal to L times I. So I can solve this for L. What do I get? The inductance of a solenoid apparently is equal to mu naught Nn, I guess. That feels wrong. Oh, what am I missing? Good grief. Kind of important. A. Yes, I missed the A. All right. I think we can simplify that further. If we write it, so like there's different ways you could go here. You could write the formula, I mean that's a legitimate formula, although it's kind of a mix. If you wanted to just write it in terms of the little n, right, the turn density, this is the turn density. Per unit length. So if you solve this for big N, we get big N is equal to little n L. Or I could solve it for little n and get little n is, I already got that there. Anyway, so this would be what? Mu naught little n is really big N over L times big N times A. So I could write the formula for the inductance to be like mu naught n squared times A divided by L. I kind of like that formula. But there's about 5 different formulas you could easily write here, right? Like if you knew the radius, of the coil, right? What would then the formula be? If I knew the radius was r, it's circular, supposing it's a circular coil, then I would have, mu naught pi n squared r squared divided by L. Okay? Right. And I also find one more, this litany of unnecessarily, let me finish this litany of unnecessary formulas. So if I wanted to convert the big N to a little n, I could also write this as what? Mu naught, I'll write it up here, mu naught n squared L A, I guess. You know, there's another, I mean, you could get rid of the total number of turns and rewrite it in terms of turn density if you wanted. Fine. All right, so great. Let's just talk about how this works. So how could you make the inductance larger? I guess we could make the coil larger, right? If we make R bigger, that makes it bigger, right? We could make L, looks like if we make L shorter, well, the trick though, I mean, these formulas are a little bit deceiving, right? If you make L shorter while maintaining the number of turns, that might be a kind of like tricky thing to arrange, right? So in some sense, like, this turn density formula here is maybe like the most I mean, this is kind of a good formula to analyze inductance by, because assuming uniform turn density is kind of a reasonable assumption that you could maintain across a variety of geometries for the inductor, right? Because just the number of turns per unit length, that's just kind of how you're winding it, right? It seems somewhat reasonable to me that you could maintain that turn density for different setups. This, on the other hand, yeah, it seems like if I make L really short, it can make the inductance really big, but the devil's in the details of how that goes, right? Because then I've got to make the same number of loops over a much shorter length, and then I'm really getting outside the region where the approximation that we're using is reasonable, right? Because this is only a good approximation of the flux through each loop in as much as each loop is close to the center of a very long solenoid. Otherwise, the magnetic field actually drops off due to edge effects, right? So I need to do more math to figure out a really short loop inductor. Anyway, this one here is kind of more to the point. We can either make the length longer, keeping the same turn density. That would give us a larger inductance, or we could make the area, bigger. And apparently it's linear as long as we maintain the turn density. If we double the area, we double the inductance. If we double the length, we double the inductance. So, okay. Now that we have that, you're like, well, that's great, but why do we care, you know? So let's connect this together with, I guess I should make this remark. If you want to, you can write the permeability of free space as 4 pi times 10 to the minus 7th, and the units work out to henries over meters. We write a capital H for henries. Does this make sense? I don't know. How did mu naught appear? We had what? B is equal to what? Mu naught I over, what was it, 4 pi r squared. I'll put the vector here. What was it? dl cross r hat, is that right? I'm pretty sure that's right. So r hat, of course I got it wrong last class and you guys didn't correct me for the whole class. So, I mean, I don't know, some of you like intentionally don't make corrections just because you want to see how long it'll take. You're bad people. You know who you are. So, in terms of unit analysis, how's that work? I guess maybe we should think about, maybe that's one thing to think about, but what about this one? Phi b, right? Equals to what? Li? So this has units of what? Like Tesla squared, well, not Tesla squared, Tesla meter squared, right? Is equal to a Henry times an ampere. So apparently Tesla could also be written as Henry times an ampere divided by a meter squared. But on the flip side, so that Tesla is the unit of the magnetic field, right? And so from the Biot-Savart law, we can also see that we've got the units for mu naught, whatever that is. And then we've got I has got units of ampere. The dl has the units of meter. The r hat is unitless because it's a unit vector. And we got meters squared downstairs, right? So if you look at all that, what do we find out? We find out that the units of mu naught are apparently equal to what? The meters squared, they be canceling. We get a Henry, amps be canceling. We get a Henry over meter. Hey, that's what I said, isn't it? So that is why the units of the permeability are a Henry per meter. Sorry, I don't do that kind of thing in here too much. I really feel this kind of calculation is really more of like a physics 201, 202 type discussion, so I don't typically take the class here, but this stuff does matter, you know? All right, so let us get back to the start of all this. By definition, so I want to talk about inductors and circuits. So we'll start with writing our fundamental relation, which is that phi b is equal to Li, right? So that's the magnetic flux through a given, coil or series of coils, right? And then, what can I do here? How do we get the voltage through the coil? Remember, Faraday's law says what? Faraday's law tells me that the voltage induced in the coil by the changing magnetic field is minus d phi b dt, right? But I can also do what? I can differentiate L times I, right? Now, I suppose in principle, we could come up with an example where the geometry of the coil was changing with time, right? Such that the L actually was variable. No? Why not? I mean, maybe the circuit is made by something that's moving, and you don't have a choice but for it to vary, right? Because really, as soon as you have a loop, it has an inductance. Okay, so everything has a capacitance as well, right? If I have two charged plates, even if I'm not trying to build a capacitor, there's an intrinsic capacitance between those two, physically adjacent metallic whatevers. It's also true of wires in a circuit, whether you like it or not. Once they get really close, there's a measurable capacitance that you have between those wires, and it will affect the circuitry. This is an issue, right, with like microprocessors, where things get so small that you can't help but have capacitance that is troublesome between wires that are close by. Similarly, if you have a loop, it has an inductance, whether you like it or not, all right? And once you have a loop, you have an inductance, and if you have a changing magnetic flux through the loop, you induce a voltage, right? This is why, if you take your grandma's, nice, whatchamacallit, china cup that's got that pretty, painted gold rim around the top of it, and you put your tea in there or whatever, and you put it in the microwave, which, by the way, creates changing magnetic and electric fields through something called a magnetron. It will burn the decorative gold conducting loop that's on that mug, right? Yeah, I've seen it's done. I didn't do this, but I know it can be done, right? In fact, many things you can microwave and find out that there's current loops inside, right? If I can find my extra microwave at home, maybe I'll bring it in. We'll do some of this sometime soon. I need to find a spare microwave that we can mess around with one day, right? I never do lab. We should do this lab. This is the only lab I'm interested in.
I have one in my dorm.
Right? You have one in your dorm?
Yeah, school property. That works.
It's school property. That seems. I mean, I guess I could steal the math department one. No one, although they probably, it's giant though, is the problem. We did, our previous microwave before we got rid of it, it was towards the end of its life, it would turn on with the door open. Yeah. Just, it didn't, whatever it was, you know, the turn off when you open the door, it just was not working. So you could get a dose. But anyway, oh, on this point, you guys know about the YouTube channel by Styropyro? Yeah. He recently made a macrowave, a 20,000 watt microwave.
I would recommend watching it. It's amazing.
It is. Yeah, that guy, I like that guy. He's good people. I love his like cheerful disclaimers at the start about death and mayhem and so forth. And it's just fun. Anyway, so this is, but okay, so my digression aside, L is not a function of time, right? So for the sake of common human decency in this course, unless I specifically engineer a problem to force this issue of calculus upon you, the inductance is not a function of time. If it was, we'd have to go back to here and deal with it there, all right? Just like in Newton's law, if you have a mass which is variable with time, you have to go back to Newton's second law and deal with the issue there, right? Okay, anyway. So there it is. The voltage induced by an inductor is equal to minus L di dt. So what that means is that the voltage on an inductor is proportional to the inductance times the time rate of change of the current. If you have current which is not changing, right? If the current's not changing, the voltage on the inductor is 0, right? On the other hand, if the current is changing, then the voltage on the inductor can be non-zero, right? So, yeah, that's pretty much it for that.
Steady state for an inductor would just behave like a short circuit?
Yes, a steady state for an inductor is like a short circuit. So inductors and capacitors are exactly backwards. So like when you, let me make a picture actually, okay? So suppose we have a circuit. That's a good question. Let's talk about it. So we have a circuit. We'll put a resistance in each, right? And we've got a switch. We're going to open it. And then at time 0, we're going to close the switch, all right? Well, I'm going to use a V this time, V naught. Voltage source, V naught. All right. So we close the switch at time 0. Let's contrast the difference. When we close the switch at time 0, right? Then what happens is current starts flowing, right? And initially the capacitor is uncharged, right? There's no electric field between the plates. The electric field between the plates of the capacitor can't suddenly go from no field up to a finite field in infinitesimal time. So it takes time for the electric field to build up between the plates. As that electric field builds up, the voltage and the charge, the voltage between the plates and the charge stored in the capacitor increases, right? And as that increases, the current decreases until as time goes to infinity. So t goes to infinity, the capacitor is open circuit, right? What happens at t equals to 0 though also? T equals to 0 plus, capacitor is a what? What's called a short circuit, right? Effectively, when you close that switch at t equals to 0, it's as if there's just a wire across the capacitor, just letting the current just flow, all right? None of the voltage is dropped across the capacitor, but the current is flowing at its maximal amount, which would be V naught divided by R at time 0 and a smidgen, right? As time goes on, the capacitor charges up, the current eventually goes to 0. The other circuit's exactly the opposite story. All right, so at t equals to 0 plus, the current is approximately 0. So the inductor is like an open circuit, right? It's like an open circuit. It has to be this because the magnetic field in the inductor before you close the switch is 0. And you can't have the magnetic field go from nothing to a finite value in an infinitesimal time. So it must be that the magnetic field in the inductor right after you close the switch continues to be close to 0. And the magnetic field in the inductor is closely tied to the amount of current that's flowing through it, right? Because like if the magnetic field is 0, well, the current's also 0 by that relation, right? So the current's 0 as we close the switch. Then as time goes to infinity, right, then the current goes to what? Just V0 divided by R. That's the steady state current. And the inductor is like short circuit. So they're, they're really dual, right? Are we good? Yes, no, maybe so? Okay, so the fundamental problem to solve for an inductor then is the RL circuit, right? So let's look at the RL circuit and see if we can solve it. Let me erase this business over here. So all these formulas I'm erasing at the moment, they don't really matter for a circuit. If you know the inductance, right? What the particulars are of the geometry which give rise to that inductance is somewhat immaterial, because you can completely understand the behavior of the inductor in the circuit just by the inductance, right? That's kind of part of the point of this, is to just look at one single number that relates the proportionality of the magnetic flux to the current. Okay, anyway. So example, what are we on here? 2, 3, I don't know. What do you guys want, 2 or 3? 2? All right. So suppose this is the situation we're up against, all right? We've got a voltage source V0. I've got a resistor R, and then I've got a switch, all right? I've got an inductor over here with inductance L. All right? And I'm going to close that switch at t equals to 0. In just a bit. Okay, so basically at t equals 0. So what is what's the deal here? Well, we have V0 minus the current times R minus L di dt is equal to 0. Because if the current flows like so, right, we know the voltage drop on the resistor from Ohm's law, and we just derived the voltage drop on the inductor is minus L di dt. And what are we up? Well, what are we up against here now? Looks like, as usual, a differential equation. So if I rewrite this in standard form, I've got like di dt plus R over L times I is equal to V0 over L, I suppose. Right? What kind of differential equation is this? First order linear, that's right. So that's important in terms of the theoretical aspects here, because if I was to add additional voltage sources here, I could figure out what the net current was by just finding the response from each voltage source and then just adding them. Supposing they were in series, it would be analogous to putting multiple forces on like a spring or something. Anyway, let's just solve this thing. So how do I solve it? Integrating factor, I like it. So the integrating factor, I'll use a mu for it since we've already got I for something else here. So it's the exponential of the integral of the coefficient of I, which here is RL over L dt, which of course just gives us e to the, RT over L, I suppose. Now, great. So multiply the given differential equation by that. We've got e to the RT over L times di dt plus R over L, e to the R over L times t times I is equal to V naught over L times e to the RT over L. So if the integrating factor works, we should have the reverse product rule at this point. Do we? Is this the product? It is. This is d dt of the integrating factor, which in this case is RT over L, times the current. If you differentiate that, the product rule gets you back to the line above. So we call this the reverse product rule. Yeah. On the other hand, that's equal to V naught over L e to the RT over L. And then I integrate, right? So if I integrate both sides there, what I get is I get e to the RT over L times I is equal to, let's see, what happens when you integrate the exponential? What do you do? We get the exponential, right, divided by the constant in the exponential, which in this case is R over L. Right? So that, and then plus a constant, which I'll call C1. So then what? Multiply by the integrating factor, and that gives me the current as a function of time is equal to V naught over R. The L's be canceling. The exponential cancels. Plus C1 e to the minus RT over L, because I divided by the integrating factor. Now that C1 is a constant, it shouldn't be in the answer. We should fit the function that we found. We need to fit it to the initial conditions, right? So let's fit this to the initial conditions. How do we do that? What is the initial condition? What is I of 0 equal to? No. 0. Remember, so the magnetic field before is 0. The magnetic field after I close the switch still has to be 0, approximately, for a very short time. So that's why, maybe I should say 0 plus or something, just to emphasize it's slightly after, I don't know, whatever. If you want, I can introduce some epsilons and deltas and make it more precise, but you do not want me to do that. No one wants to see that. So I of 0 is V naught over R plus C1. That's equal to 0, so therefore C1 is minus V naught over R. Hence, we find the current as a function of time for the RL circuit is simply V naught over R times 1 minus e to the minus t over tau, where I have introduced tau as equal to L over R. This is the so-called time constant. Time constant for the RL circuit is the inductance divided by the resistance in the circuit. The bigger the inductance, the longer the time constant. The smaller the resistance, the larger the time constant. The larger the resistance, the smaller the time constant, right? In the story, we've kind of told the story before, but for the charging capacitor, we found a similar formula, right? It also involved the time constant, and the time constant there was RC, right? Do you remember what the formula was? We derived it before. I can't remember. I think it was it Q of T is equal to, what was it, like V naught over C, 1 minus e to the minus t over tau. But there the tau was equal to RC. I think that's what we got. That makes the initial charge 0 on the charging capacitor. And then as time goes to infinity, you get V naught over C, which is to say that the capacitor is fully charged. This is the formula for the circuit, the other circuit I've got over here, that one. We worked that out at another time. So this, the charge. So you can contrast the formulas. It's very much similar, but the difference is, of course, that that's for charge, right? And this is for current. Of course, the charge and the voltage are related. How so? What was the deal with what's the relation between capacitance and charge? Say that again? Q is CV. All right, so V on the capacitance as a function of time would be what? It's Q over C, right? Oh, did I do it wrong?
Isn't it just Q naught top 1 minus T over tau?
Well, Q naught 0. You're saying I should have CV naught? That's probably right. It's been a minute. I don't. Would that make more sense to you? I mean, you're right. Capacitance is charge. Capacitance was charge over voltage, right? By definition. That the definition of capacitance is that, right? If that's the case, then the formula for Q must have units of like CV naught. Yeah. My apologies. We fixed it. Yeah. So notice that a close cousin to this formula, divide by C, and you've got the voltage on the capacitor, right? So the voltage on the capacitor as a function of time is V naught times 1 minus e to the minus t over tau, right? Just dividing by C. And that formula I just wrote up there, as time goes to infinity, the voltage goes to V naught, right? All of the voltage is across the capacitor. Because the capacitor is fully charged, there's no current flowing, right? It's all dropped across the capacitor. But that's the formula for voltage, whereas this is the voltage for current. So current for the inductor is like voltage for the capacitor, and vice versa. That's the mathematics. So, and the time constant, you see what I'm doing here? I'm just rewriting e to the r, I'll write in here, e to the RT over L is equal e to the t divided by L over R, right? So we just call that thing the time constant. And so like I told you guys before, after about 5 time constants, the circuit is done adjusting, right? It's essentially to within 1%, it's to the steady state of the circuit, right? After about 5 time constants. So everything dynamic in the circuit's happening in those first 3 time constants mostly, all right? So, any questions? So I'll probably try to solve example 80 next class. That's on page 107. It's got like 2 resistors and an inductor. We solved something kind of like that with capacitors before. It took us a while, but we'll get it. Something struck me. It's been a while since I taught this course, but all of a sudden I noticed it doesn't seem like we ever ask about equivalent inductance. Like, why don't we talk about that? It's calculated the same as resistance, so it's not exciting. That seems exciting, though. Some people need review of the equivalent resistance, right? What's that? I should do a class on it. All right, so let me tell you guys a little bit more about where we're going here. So past this, I need to define mutual inductance. We'll do that sometime soon. Mutual inductance is actually maybe more important than self-inductance in some sense. Many applications of inductance involve mutual inductance, which is when mutual inductance is when the magnetic flux through one coil, it's not due to the current in the coil. It's kind of due to the current in another coil. So like you're creating a magnetic flux through one coil from a current in another coil, but they're coupled. So anyway, we should look at that. We also, of course, need to look at like how do we quantify the energy in a magnetic field. I think I've got enough time for that. Let's do that. So magnetic energy. Wait a minute, what am I doing? We should end class early because what? What happened? What happened last night? Why did we even have class today? Why were classes not canceled today? We can celebrate over a sports ball event. Surely we can celebrate the lack of the fall of Western civilization. I mean, I don't know. I mean something.